So, the final technique that we will talk about in this chapter of spectroscopy techniques is nuclear magnetic resonance spectroscopy. Okay. Now, this is something that some of you may have had an experience of in medical imaging. For instance, when X-ray techniques in medical imaging do not give the intended information, very often the doctors prescribe you to go and see or go and get an NMR scan or MRI scan, they call it magnetic resonance imaging. It is nothing but the same as nuclear magnetic resonance. So, what is done in this case is that we use radio frequency radiation to induce transitions between nuclear spin states of samples in a magnetic field. Now, you know that the atomic structure, you have nucleus in the center, and if there is an unbalanced number of neutrons and protons, the nucleus will have a spin. The greater the imbalance, the greater will be the spin quantum number. We call it the spin quantum number of different nuclei. I will just show you the examples of different types of elements in just a minute. So, when there is an imbalance between neutrons and protons, you get a nuclear spin. Okay. So, what happens is when you apply radio frequency radiation, this spin may change as a result of absorption of that radiation. So, the change in spin is characteristic again of a certain energy being absorbed, or in other words, if the spin wants to come back to its original ground state, it has to re-emit that energy, and detecting that re-emitted energy will give you an idea about what kind of element was actually present in your sample. Same sort of analysis as we had in the other means of spectroscopy. All you are doing is introducing radio frequency waves which generate a different kinds of transition in your species that are present in your sample. So, once again to recap, atomic absorption and ultraviolet visible light led to promotion of outer shell electrons to higher orbitals. Okay, absorption of that radiation led to outer shell electrons getting promoted to higher orbitals, whereas your IR radiation had energy only capable of introducing vibrations, molecular vibrations. Now, we are talking about radio frequency waves that have much longer wavelengths. As a result, the energy level is even lower, and they are not able to induce all those kinds of transitions that the previous examples had. So, here we are only inducing transitions which are related to spin of the nuclei when you have an electric field applied to the system. So, this is most useful for determining structure of molecules because of different atoms in a molecule which experience slightly different magnetic fields, and therefore transitions at different resonance frequencies in a nuclear magnetic resonance spectrum. Okay. So, if you are again able to isolate the frequencies at which the absorption takes place, you can then characterize the type of element that you have in your sample. So, again if there are interactions happening between different nuclei, there will be splitting of the spectral lines, and that will give you information about how close the atoms are in a molecule. Okay. So, I will show you the examples of what happens in all these cases in just a minute. So, again as I said, nuclei with odd number of protons or neutrons or both will have an intrinsic nuclear angular momentum or nuclear spin. Okay. So, for example, if the number of protons is even, number of neutrons is even, the spin quantum number is 0, okay, such as what you have for carbon, oxygen or sulfur. If the number of protons is odd and neutrons is even, then the quantum number is half in certain cases, like in the hydrogen atom, fluorine or phosphorus. Okay. Now, if there is a greater imbalance, again with odd and even combinations, you can have a higher spin quantum number 3/2, for example, in the case of boron, chlorine, bromine, iodine, etc. Okay. You can also have even number of protons and odd number of neutrons generating similar spin quantum numbers. Okay. And in some cases you have odd number of protons and neutrons, and you get a spin quantum number of 1 in that case, like in the hydrogen molecule or in the nitrogen molecule. So, when a nucleus with a spin that is not 0, that means any nucleus which does not satisfy this even number of protons and neutrons condition, okay, when such a nucleus is placed in a magnetic field, okay, the nuclear spin can either align in the same direction of the magnetic field or reverse its direction when the external magnetic field is applied. Okay. So, where is this system placed? Now the system is placed in a magnetic field where the nucleus can have either a alignment in the spin along the magnetic field direction or reversal in the spin as compared to the magnetic field. Now nucleus that has spin aligned with the external field will have lower energy than when it has spin aligned in opposite direction to the field. So when you are applying the electric field and the nucleus gets a spin in the same direction, it is present at a lower energy level as opposed to the other case, which is obviously the opposite, where the nucleus spin is opposite to the external magnetic field. So these two alignments have different energies. An application of magnetic field results in an energy level diagram, which is shown in this case. For example, when you have no field, right, you have a certain energy level for your nucleus. When you apply a certain magnetic field of strength H, you could have two states. One is the lower state, which happens when the nucleus spin is in the same direction as the field, and a higher state when you have nucleus which is spinning in the opposite direction as the aligned magnetic field. Okay. So now this gap that exists between the low energy state and the high energy state, okay, it corresponds to radio frequency. Okay. So if you want to actually bridge that gap, it can happen either by absorption of radio frequency radiation, which will bring this up to that level, or it can happen because of emission of radio frequency radiation, which will bring the higher energy nucleus back to the lower energy level. Okay. So this gap is in the radio frequency range, and based on the different types of elements that are present in your sample, right, each gap between the high and low energy states will be having a very discrete value, and that discrete value will obviously have a very single set radio frequency. And so with the use of radio frequency radiation of nuclei that are subjected to magnetic field, you can then analyze what type of nuclei are generating those transitions. So in medical imaging, what happens? You have, for instance, if you want to do an imaging of your knee, right, what they do is they envelop your knee in a very sophisticated, anyone has got an MRI scan done? Yeah, it is a very scary experience, because they send you into this room where there is absolutely no sound coming in, it is a soundproof room, and then they make you lie on this bed and send you inside this instrument, and they actually envelop the location which is being scanned, or totally encase it. I had my knee scanned, so I have that experience. So and then what happens is the instrument then applies a very high magnetic field or specific ranges of magnetic fields to your location which is getting imaged. So what is there in our system? We have water, right, and we have calcium carbonate in our bones. Okay. So there are very specific species inside. If you for example, if you want to do bone analysis, you are basically looking at calcium, or maybe you are looking at different states of your carbon and oxygen that are present in the system. Okay. So based on that, the radio frequencies that are generated in that magnetic field or absorbed in that magnetic field are then analyzed to detect the presence of the elemental species, and in our case, in the medical imaging case, the spectrograph is then converted into an image. Okay. For example, if your bone density is low, or if you have had a fracture in your bone or a tear in your muscle, even that can be actually imaged quite easily with a MRI scan. In the case of X-rays, your muscular tissue cannot be easily imaged. You can image bones because bones are fairly significant in terms of density as opposed to your flesh. But in MRI, you can actually make distinctions of your flesh also. You can actually look at muscular orientations, muscular tears and things like that also. Okay. So in MRI scans, what we are simply doing is converting this entire exercise into an image which is representative of the phenomena that is being observed inside your system. Okay. So again, a nuclear spin. So for example, if you have a spinning proton, right, the spinning of this charged particle, right, there will be some sort of a nucleus with an odd atomic number, has an odd mass number, has a nuclear spin. the spinning charged nucleus generates a magnetic field. So, any charged particle when it has a spin, it will generate a magnetic field. So, when you place this charged particle inside a magnetic field, okay, there can be either alignment with the external field or opposition to the external field. Okay. So, spinning protons when they are placed in external field start acting like magnets. You have all used horseshoe magnets, so you will understand what this is. So, for instance, if this spinning magnet which is a spinning proton is placed inside this horseshoe magnet, your twisting motion may actually happen because of the external field being different compared to the internal field, or you can get an alignment in this configuration where the north pole of your proton magnet, the small bar magnet, is aligned with the south pole of your external field, and south pole of your proton is aligned with the north pole. That is a stable configuration or lower energy configuration. But if this twisting leads to the other configuration, that is the north north and south south, you know that like charges will repel, as a result of which this configuration will be less stable. In other words, it will be the higher energy configuration. To make this stable, what needs to happen now? Radiation needs to be emitted, some energy needs to be lost to the surroundings to bring it back to the stable state, okay, and that emission is in the radio frequency range. So, again magnetic fields with spinning nuclei, as I said, align either with the field or against the field. A photon with the right amount of energy can be absorbed and cause the spinning proton to flip. Okay. So, the proton is spinning either with the magnetic field or opposite to that. So, if you send in a radio frequency photon, that means a particle, light particle, into this system, it can get absorbed by the system and cause the spin to change directions. Okay. So, these absorptions are generated at specific frequencies for specific elements that you have in your sample. So, carbon will have a specific frequency, aluminum may have a specific frequency, silicon may have a specific frequency, and so on. Okay. So, these circulating electrons create an induced magnetic field. So, we know that it is not just the nucleus in the atom, right. We have electrons also which are orbiting the nucleus. So, when you have this magnetic field which is causing this nuclear spin to change, okay, it has some sort of an effect of shielding by the externally present electrons that are present in the system. So, around the nucleus you have electrons. So, the electrons can create an induced magnetic field that opposes the external field. So, magnetic field strength must be increased for the shielded proton to flip at the same frequency. So, because of the effect of the electrons, you have to increase the strength of a magnetic field to cause the spin transition of your element to happen at the same frequency level. Okay. So, again this is a example where you have a proton, just a proton which absorbs at a frequency of 60 megahertz. Okay. A shielded proton does not feel the effect of the same magnetic field. So, here the magnetic field applied is 14,092 Gauss, okay. But a shielded proton, because of the effect of the electrons around it, does not feel the same level of magnetic field being applied around it. So, because of that, it does not really absorb this radiation coming in at 60 megahertz frequency. Okay. Now, in the other case, if you increase the magnetic field by the amount that the electrons actually reverse that field, then it will start absorbing at that frequency. Okay. So, what you need to understand is what is the influence of the electronic clouds that are over this sample. So, now what will happen if I go with samples that have much bigger atomic structures? The interference by the electronic cloud will be more. So, I need to actually make adjustments in my external magnetic field to cause my proton to absorb the radio frequency radiation. So, the energy of the NMR transition, as I said, depends on the magnetic field and the proportionality factor for each nucleus, which is called the gyromagnetic ratio, gamma. So, frequency of a transition is given by, of course, this is not V, it should be nu, frequency is written as nu. Okay. So, nu is given by gamma h by 2 pi, where gamma is the gyromagnetic ratio, h is the applied magnetic field. Okay. Now, what happens is, as a result of the absorption or emission of the radiation, right, your frequency can undergo a shift. So, frequency is generally represented in terms of chemical shift, which is given as this shift is given as frequency of the sample expressed as a difference with the frequency of a reference, and the reference typically is taken as tetramethyl silane or TMS, which is unreactive with other organic compounds and gives absorption which is mostly shielded. Okay. So, this is a typical reference frequency that is taken in your NMR systems, and you represent the frequencies of the sample as a function of this frequency of the reference, that is tetramethyl silane. So, this is your NMR spectrometer. So, this is a sample tube which is encased inside a very powerful magnet. Okay. So, what happens is you apply the magnetic field and then you have the radio frequency transmitter, right, that is transmitting the specific radio frequency radiation, and the absorption of that radiation is then detected by the detector, and you get the absorption spectra of the absorbance as a function of the applied magnetic field, absorbance as a function of magnetic field. So, this is again the instrument that is there. So, you see here, this is the overall system in which you have the magnet as well as the introduction of the sample inside, and the remaining are basically generators of the kind of magnetic field that you have. If you go again inside an MRI lab of a hospital or of a big laboratory, you will see that the instrument is fairly large, okay, and each instrument is capable of producing different levels of magnetic fields. So, in the experiment what we do is we keep the external magnetic field constant and vary the frequency of radiation to see absorption. It is as simple as that. So, for a constant applied external field, we vary the radio frequency radiation that is sent into the sample to look at specific locations at which absorption takes place, and that this is detected by the detector. So, the other way is to keep the radio frequency constant and vary the field until splitting of the spin states corresponds to the energy of a radio wave. What does it mean? Splitting of spin states means there is a low energy state and a high energy state, right, and that corresponds to the energy of a radio wave. So, incoming energy of a radio wave is equal to the energy difference between the low energy state and the high energy state. So, that is the other way of actually doing the experiment. Okay. In new instruments you get an intense radio frequency pulse to excite all the nuclei simultaneously, and then we do a Fourier transform to extract all the informations together. Okay. In the older instruments, again you had to send in one radio frequency at one time and analyze each element separately. In this case, in the new instruments, what you are doing is sending in a strong radio frequency pulse that is combination of several different frequencies, okay, and you are then doing a Fourier transform of your detected signal to separate out all the elemental compositions that may be there in the system. Now, the signals can be interpreted in several ways. The number of signals show how many different types of protons are present. Okay. The number of signals show how many types of protons are present. The location of the signals can indicate how shielded or de-shielded the proton is. Okay. So, location implies position with respect to the magnetic field. So, the higher the shielding, the greater will be the applied magnetic field. Okay. Lower the shielding, the lesser will be the magnetic field. The intensity of the signal shows the number of protons of that type. Okay. If there are more number of protons of a specific element, then you get higher intensities shown by the spectra that you see from NMR. Signal splitting shows the number of protons on adjacent atoms. Again, I will show you some examples of signals that will make it clearer. So, this is the NMR plot. What is plotted here is in terms of the increasing magnetic field strength. As I said, when you have less shielding, you get a peak earlier, when you have more shielding you get a peak later. That means at higher magnetic fields you are producing the peaks when there is more shielding in your system. So here a very simple structure is chosen, that is CH3OH. What is this? Methyl alcohol or methanol, right, CH3OH, or otherwise known in newspapers as hooch, right. This is a major killer in our country, right. A lot of people consume this thinking that it is ethyl alcohol, but this is poisonous. It can actually affect death in very fast time. So this is CH3OH or methanol, and you can see here that the carbon is better shielded in this case because there are several hydrogen atoms around it. Okay. In this case your hydrogen is exposed and not really getting shielded very well. Okay. So what happens is the peak shows a upward or upfield higher strength of the magnetic field to have the same level of to show the same location of the atom. So if you consider a specific frequency in the NMR instrument like 300 megahertz, what we are trying to see is how does the increased shielding get represented in the typical NMR spectrum. As I said earlier, NMR spectra are typically represented in terms of the peak shift delta, which is represented as the difference of the frequency of this proton minus the frequency of the reference sample, right. So here for instance the frequency in hertz is also given and the shift delta is also given. So when you have more shielding you show lesser shift, and when you have lesser shielding you show a higher shift in your NMR spectra. So for instance in chloromethanes, so here this is just methane, now you have a single chlorine replacing the hydrogen atom, here you have 2 chlorines with the hydrogen atom, you have 3 chlorines here. So all you are doing is increasing the level of substitution of hydrogen with chlorine. So you are forming different types of chloromethanes. So each chlorine atom added changes the chemical shift of the remaining methyl protons by about 2 to 3 parts per million. Why? Because more and more electronegative atoms are shielding more and giving larger shift values. Okay. So again your shift is changing from 0.3 to 0.2 to 3 to 5.3 and finally to 7.2 as you replace your hydrogen with chloride atoms in the case of chloromethanes. So what will happen is when you try to detect chloromethane with NMR spectroscopy, you will be able to detect the extent of chlorine present in the system by looking at the positions of the shift. Okay. So there is an increase in chemical shift when you have additional electronegative atoms here. In this case chlorine obviously is an electronegative atom and you are tending to shift more and more, and that helps you to actually understand where to detect different states of chlorine which are substituted in the methane structure. Now in some cases you may come across NMR instruments that are characterized as MAS or magic angle spinning NMRs. So what we do here is this, we spin the sample usually at a frequency of 1 to 130 kilohertz, okay, at the magic angle theta m, which is approximately about 54.74, okay, with respect to the direction of the magnetic field. So we spin, we have the sample kept at a specific angle with respect to the magnetic field direction. What happens here is the normally broad lines become narrower and we increase the resolution of the spectrum. Okay. So many cases you will actually see magic angle spinning NMR being done. So all we are trying to do is we are making these frequency transitions more precise. Instead of having a broad signal we are getting a more precise signal in magic angle spinning NMR. We use this significantly in solid state nuclear magnetic resonance spectroscopy. So again just to give you an example, let us say we want to analyze calcium silicate hydrate. Okay. So what we have with respect to calcium silicate hydrate are different types of states. as the hydration progresses, there is an increased degree of chain linking in the CSH structure. Many of you would have understood the CSH structure is actually composed of sheets of silicates. The greater lengths of the sheets are created by progressive states of hydration. Okay. So, a frequency of 59 megahertz for silica is chosen and a frequency of 130 megahertz is chosen for alumina. So, we can either do silicon NMR or aluminum NMR at different frequencies to try and understand the state of the CSH in the system. So, what happens is the software can actually help us to deconvolute the NMR spectra, okay, and analyze each individual components separately. So, just to give you an example of how aluminum NMR spectra is used to actually understand the structure of calcium aluminosilicate hydrate. Okay. So, there are 3 different systems which are given here, and what is represented in the x axis is the aluminum chemical shift. Okay. So, at different aluminum to silica ratios, you see that the chemical shift is actually changing, or the peak intensity is actually changing as you increase the aluminum to silica ratio from 0.12 to 0.19. Okay. This is for a measurement on calcium aluminosilicate hydrate at a water cement ratio of 0.7. Now, this is again at 0.95, and again you are seeing an increase in the intensity of the peak that is located at a specific chemical shift that corresponds to the state of the aluminum present inside the calcium aluminosilicate hydrate. Okay, we will continue from here in the next class.